I'll be happy to entertain that. Anyone? Oh, wrong class.
Hey, where do you go to grad school at?
What's that?
You go to grad school?
Here?
UTSA?
Uh-huh. Yep.
And you went to the school of science, right? You graduated?
Yes.
How'd you like
Yep.
it?
It was a long time ago. It's a long time ago. No, I mean, but a lot's changed since I was there.
I remember coming here in 2000. It's so different now.
Yeah, that's when I started here. So, yeah. It was fine. I mean, it was small.
It's considerably different.
Well, I don't know how big the math department is. When I was in grad school, there was 4 of us that did the pure math program. There's 4 of us that graduated together. So like we had to, almost every semester we had to petition for every single class to be offered.
Yeah.
Yeah.
That means like there's not enough people, so he had to like go and physically say, we need this so I can create a graduate plan for myself.
Yeah, exactly. So it was 4 of us that had to stick together. None of us could fail.
How much further is the doctorate after this now? Like, if you went
For
your
what?
If you went for your doctorate to write a thesis and
Well, it would depend on what I would do it in.
you'd have to like, find something that you wanted to actually.
Yeah, well, the reason I didn't do it is because there wasn't a doctorate program in math in San Antonio at the time. Now you can get a doctorate in math education, but in pure math it's still not available.
Unless you like come up with some very groundbreaking stuff.
Yeah, I mean you could do that. Yeah,
Geist or something
Yeah.
inside of you somewhere.
yeah. I don't really have a desire to do the PhD in math.
Well, I was talking to a PhD the other day, and he was like, you really should consider the graduate program for chemistry or the doctoral program. And I was like, it's just so far away.
Well, here's the thing. For me, if it was in chemistry or biology or something like that, I would definitely go after it. But in math, you have to have original thought. Like it has to be original. And you're talking about,
Extremely hard. Everyone's
it's
already
very
been
difficult.
thinking about it for quite a few hundred years now.
Yeah. So I had a buddy of mine who finished the master's, and then he went on to go pursue his PhD. And he transferred out to UT Austin, and he must have worked on just getting to the question for like 6 years before he even got to the point where he could even try and do something. And
Commitment to a craft.
yeah, but I don't, once I got to the point in my life where I had family and, wife and kids, then it became less.
Normalized right now.
Yeah.
You just like think of the move you went through right now.
Yeah.
How caustic that was to everything.
Yeah.
To imagine trying to change it. To
Yeah,
a doctoral
yeah,
lifestyle.
no. I enjoyed my master's program. I was single. I had a lot of time, Yeah.
I left
So.
I left a job at UPS. I worked at UPS on the MD-11 player line.
Uh-huh.
Come back to college because I got asked for a job, and they told me that
You need your paper. You need your piece of paper.
and I was like, well, you know what? I'm quitting. They couldn't believe it.
Really?
And
Well, if your family wants to go, they should go.
Yeah.
They should be on the
What do you got?
list.
We had a question on 7.7. It was like like 11, 13, and 15.
7, 7. 11.
11, 13, and 15.
Okay, I'll do one of those.
Okay.
Okay, I tried to start class early, but now I'm behind. We're going to start chapter 8 today, analytic trigonometry. We're going to talk about inverse functions, specifically the inverse of sine, cosine, and tangent. But I did open the floor to any questions, and I do have a question on 7.7. I've been asked about number 11, 13, and 15 from the homework, so I'm just going to do 13. Number 13 says, for what number, I'm not going to write it down because it's like a word problem. It says, for what numbers x, where x is between negative 2 pi and 2 pi, does the graph of y equals secant x have vertical asymptotes? Okay, so it says, look, focus all of your attention between just negative 2 pi and 2 pi. If you were to graph this, find all the values of x where this would have a vertical asymptote. So what I'm going to do is I'm first just going to rewrite this as 1 over cosine x because that's what secant is, right? And then I'm just going to say vertical asymptotes will occur whenever cosine is 0, right? If this cosine is 0. So I ask myself, when is that equal to 0, right? Now I go to my unit circle because I love my unit circle. And I ask myself, where is cosine being 0? That means where is the x-coordinate 0 on this circle? So that's going to happen here and also here, right? So let's look at that. That happens at pi over 2, right? At 3 pi over 2. So that would be, let's see, if this is pi, here's pi over 2. So I'm going to have a vertical asymptote here. I'm also going to have another one at 3 pi over 2. And then I don't need to keep going because it's only asking between negative 2 pi and 2 pi. But I do need to go negative. I need to look at some negative angles. So negative angles would be me going this way. And that would be at negative pi over 2 and negative 3 pi over 2. Would be two other places. Does that help? Whoever was asking? That does, yes? Yeah, yes. So the answer, there are, what, how many answers? There are 4 answers. Pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Those would be the values of x that are between negative 2 pi and 2 pi where secant would have vertical asymptotes. And then if you do number 15, it's the same question, but they ask you to look at tangent. Tangent is sine over cosine, right? So wouldn't you have the same answers? Sine over cosine, you're going to ask yourself the same question. When is the denominator 0? So you're going to be saying when is cosine 0. So number 15 should have the same solution as this one. Number 11, they are asking about where does secant equal 1? Where does secant equal 1? Same interval, where is secant 1? Well, if secant is 1, that means I need 1 over cosine to be 1, right? And the only way this ratio can be 1 is if cosine is actually 1. And where's cosine 1?
0 pi to 1.
Just here, right? And then you have to get all the way back around. So you would say 0 or all the way around once, 2 pi, or you could go backwards, negative 2 pi. So there would be 3 answers. I hope that clears that up a little bit. All right, good. Let's get into inverse trig functions. Now, before we can actually do inverse trig functions, we all need to understand what in the heck an inverse function is. And this can be somewhat complicated. So I'll take even one more step back and make sure we all understand what a function is. Okay, a function takes a single input to a single output. Now, that's just a very loose definition of what a function is. It takes something in, spits something out. What it cannot do is take something in and spit two different things out. So when we first learn about functions in college algebra, sometimes they show you like these two sets, and then they say, okay, if this is 1, 2, 3, and let's say this is, I don't know, 4, 5, 6, they say, what if 1 goes to 4, and 2 goes to 5, and 3 goes to 6? And they say, is that a function? And you all say, does every single input go to exactly one output? Yes. So you say, yes, that's a function. Then they give you another example like this. 1, 2, 3, 4, 5, 6. And they say, what if 1 goes to 4, and 2 goes to 4, and 3 goes to 6? Is that a function? Yes, it is. So I'm going to put F here for function check mark. That is a function. Is this a function? Yes, because for every single input, it goes to one place. It's okay if two inputs go to the same. You just can't have one input go to two different places. That would be this picture. 1, 2, 3, 4, 5, 6. What if 1 went to 4 and then 1 went to 5? Not a function. And then 2 could go anywhere. That would not be a function. And the only reason it fails to be a function is because 1 goes to two outputs. Right? So no function here. Function takes a single input to a single output. Now, when we graph functions, there's an easy way when we look at a graph for us to know if it is a function. Do you remember the test we use when we look at a graph to determine?
The up and down.
The up and down, the vertical line test, yes. Does that ring a bell, vertical line test? So given the graph of a function, given the graph, let's say not of a function, given the graph of a relation, okay? A relation is different than a function. A relation is not as strong of a condition. A function is something that satisfies this. A relationship doesn't have to satisfy that one input goes to one output. So if I graph something that relates x and y to each other, then the vertical line test is used to test whether or not it's a function. So given the graph of a relation, we use the vertical line test. Which I might refer to from now on as VLT, vertical line test, to check if it is a function. And I should be a little more specific, a function of x. So a couple of examples. Is a line a function? Yes, because how does the vertical line test work? I don't remember. Can you remind me?
If it crosses the vertical line more than once, so if it was a parabola on its side, it would fail it.
Okay, so the rule is that I need to draw vertical lines, and every vertical line I draw, I look at separately from the other, so I draw this one, I do the test. Then I move the line, do a different test. So I draw this, and the rule is that I cannot hit the graph more than one time. I cannot hit it more than once. So as long as I hit it one time, I'm good. I'm good. And that has to work for every vertical line that I draw. So that would be a function. Would a parabola be a function?
Yeah.
Yes, still, as I draw vertical lines, I'm good, right? Would a circle be a function? No, that would fail the vertical line test. Now, would it fail the test for this vertical line? When I draw this vertical line, do I hit it at all? That's okay. Okay, you don't fail the test if you don't hit it. You just can't hit more than once. I start failing the test. Let's see, when I hit this point, I still don't fail the test. As soon as I get past that, I'm going to hit 2. And that's no good. Now, why is that no good, though? Why is this test telling us it's not a function? Yeah, so if I look at this x, right, as my input, then if I go to this x value, which is back here, the output should be the y coordinate. And it's saying I have 2 different y coordinates for the same x coordinate. And that's a single x going to 2 y's, and that's no good. Okay, next one. How about, I wanted to draw another one, but how about this one? No? No. So this is not a function. So this test, you've done this in the past. In fact, when you saw this test for the first time, you probably just wanted your teacher to give you like 50 of those, make that a test, and you would have been very happy, right? Okay, that's how we check for functions. Now, how about inverses? What is an inverse of a function? Does anybody know the definition of an inverse? Or like, can you explain it to me? But like in just, layman's terms, like explain to me.
It doesn't necessarily make the opposite of it. It almost like it seems like it's almost like 180 degrees for a reflection of it.
Oh, you're talking about the picture of it. Okay, you're talking about the graph of the.
So just how to,
Okay.
explain it.
So let's try this with pictures. And I'm going to do this with, start this out, inverses. All right, we have this picture. And we have, let's go back to this 1, 2, 3, 4, 5, 6. And I'm going to draw this. Okay, is this relationship that goes from here to here, is that a function? Yes? Okay, so let's call the relationship going from here to here f as a function. You can see that this function takes 1 and it turns it into what? 6, and then it takes 2 and turns it into 5, and then it takes 3 and turns it into 4. And that is a function. Every input goes to exactly 1 output. Now, the inverse function is the function that's going to undo that function and send everything back to where it came from. So we look at it like this. It's the one that goes backwards. We use this notation, f with the little -1 up there. This should all look familiar to you. You took college algebra. So we have this idea that it should take it back, right? Now, in terms of the domain and range, okay, the domain of f is this over here, right? The domain of f. In this case, the domain of f, I'm going to put dom f for domain of f. The domain is 1, 2, 3, right? What's the range of f? What are the outputs? Ran f for range, is that okay? The range of f is 4, 5, 6. Now, if I'm talking about the inverse function, what is the domain of the inverse function? It's the range of f. See, the things that go into the inverse are the things that actually came out of f. So the domain of f inverse is this, and this right here is the range of f inverse. So we have that relationship. When you have inverses, the domain of f is equivalent to the range of the inverse function, and then the range of f is equivalent to the domain of the inverse function. They switch places. This is important because we're about to talk about inverses of trig functions. We need to understand what the domains and ranges are because they're going to switch places. We clear on this picture? Now, there is a more precise definition of inverses, and I'm going to write it up here. Okay. Given 2 functions, f and g, we say g is the inverse of f and denote it with this notation if the following two things are true. So look, the way I want you to read that is this. Let's say I give you two functions, all right? I say, hey, here are two functions, f and g. The only way you can tell me that this g function is the inverse of f is if these two things that I'm about to put up here are true. So if, this is if, 1, when you take f and you compose it with g and you plug something into that, what does it spit out? Anyone remember this from college algebra? So let's try and figure out what this is saying. This is saying if I take x and plug it into g first, that'll give me some answer, g of x, right? And then I take that answer and plug it into what? F. Plug that answer into the f function. In order for this to be an inverse, what has to come out here? X has to come back out. So think about that, the picture I just drew a second ago. Do you remember I had this thing? Where did 1 go? It went to 6, didn't it? Where does the inverse function have to take 6? Back to 1, right? So this is kind of like, okay, you plugged in 1, it spit out 6, that 6 needs to go back to 1. We need that to be true in order to call that an inverse. But there's one other thing we have to have happen. It has to work the other way around, meaning that if we start with a number over here, send it through the inverse, then back through the function, it comes out unchanged. So this, I forgot to put equals x up here, sorry. Equals x, equals x. Do y'all remember those from college algebra? Hopefully your teacher made you prove that two functions were inverses by verifying those two things. Maybe they did, maybe they didn't, but that's the precise definition, is that they pretty much wipe each other out. Okay, what about visually? If I give you something, a picture, do you remember what the test is to check to see if it has an inverse? You told me just a second ago that you had this vertical line test, and that's the way you check to see if something was a function. Do you remember the test you use to check to whether or not a function has an inverse? No? Horizontal line test? Does that sound familiar? It's the same test, but you use a horizontal line instead of a vertical line. Show of hands. Horizontal line test? Really? Really? Okay. So, well, the good news is that it's easy to do. Okay, so I can show it to you. The horizontal line test. I'll write it down here. Given the graph of a function, we use the horizontal line test to determine if it has an inverse. Now, what does the horizontal line test say? Any horizontal line I draw can hit the graph no more than one time. So is it okay if I don't write that down? It's the same as the vertical line test, but with a horizontal line instead of a vertical one. Okay, so I'm going to draw some pictures here, and you're going to tell me whether or not this has an inverse. I'll do the graphs in a different color. Okay, that's a line, right? Does that have an inverse? Yes, it does. Because if I draw any horizontal line, I'm never going to hit the graph more than one time. Parabola. No, that does not have an inverse. Not in general, because if I draw horizontal lines, I'm going to hit this more than once, right? So this right here, inverse, yes, inverse, no, right? How about this one?
Yes.
Yes? Okay. What did you say? It's not a function, but it does have an inverse. Read this carefully. Given the graph of a what? A function. Okay? You can't even talk about inverses if you don't have a function. This isn't a function. Fails the vertical line test. Yes, it passes the horizontal line test, but you're not allowed to even talk about horizontal line test unless you've got a function to start with. Understand? This here fails to be a function, and therefore the inverse just doesn't even make sense to talk about. Okay? I always put that one up intentionally because you just automatically go, oh, horizontal, yes, it's inverse, yes, but it's got to be a function. And then how about the circle? How about the circle? It's not a function. So, I mean, automatically you don't talk about inverses, right? All right, I've got some more pictures for you. You seem to like pictures. Okay, how about this one? I'm going to be a little more detailed on this one so you can kind of tell what it is. Hopefully you recognize this. Recognize that? What does it look like to you? Looks like sine x. Okay, that's what it was supposed to be. Is that a function?
Yes.
Yes. Does it have an inverse?
Yes.
How does it have an inverse? It fails the horizontal line test, right? But wait a minute. Today, this section is about what? Inverses sine. What the hell am I talking? Okay, we've got some issues, right? We've got some issues. If you look at that sine function just as it is, it's a function, but it fails to have an inverse. Right? Okay. We're going to stick with that for right now. How about this one? How about cosine? So this is cos x, sine x. This is a function, yes, inverse, no. Function, yes, inverse, no, right? You're going to fail the horizontal line test. So it appears like we should just skip this section, huh? Because they don't appear to have inverses. How about tangent? Tangent had those asymptotes. Where were those asymptotes? You need to remember where they were. This is tangent x. Where were they? Where were they? I heard it. What? Negative pi over 2 and pi over 2. You need to remember that. Okay, and this was the tangent. It looked like this. Okay. But isn't it periodic? Like it keeps doing this, doesn't it? So, interesting question. Is it a function? Every vertical line I draw hits the graph no more than one time. Okay? If I put a vertical line over the dotted line, I don't hit the graph. That's okay. I just can't hit more than once. So it is a function. How about horizontal line test? I'm going to hit a bunch, right? So I will hit, if I draw this horizontal line, I'm going to hit infinitely many times. That's what's happening here too, right? I have infinitely many places. This is bad. I don't know. We were supposed to cover 8.1 today on inverses of these, but they don't have inverses. So we'll just call it a day. Woohoo! There's got to be something going on here, right? Something has to be up here. So I think to help motivate this a little bit, I'm going to go back and I'm going to work with a function that's a little bit easier for us to understand, and then we'll get back to the sine, cosine, tangent. Let's go back to this one. F of x equals x squared. That's your basic power function, your basic parabola from college algebra. We graphed that a second ago, and we said it was a function but failed to have an inverse, right? Which is the same thing we're saying about sine, cosine, and tangent. They're all functions but fail to have inverses. So what I'm going to do now is I'm going to do something to try and illustrate why we have a problem. So if I take some inputs here and look at some outputs, let's go 0, 1, and 2. Those are going to go to 0, 1, and 4, right? Yep. The problem we have is that when I start plugging in negative numbers, where's the negative 1 going to go? It's going to go to 1. That's not a problem in terms of being a function, right? When I take negative 2, it's going to go to 4. So looking from this direction to that direction, we're good. But if I look from this direction back that direction, 4 goes to 2 places. And that's no good. That's where, see, moving backwards, this inverse function cannot be a function if 4 goes back to two things, 2 outputs. So how could I maybe do like a workaround so that this doesn't happen? Can anyone think of what I could do to somehow change things so that I don't have this problem of these things coming here and having to go back to 2 places? Don't change the function. Change the domain. Okay, so why don't you restrict me? Why don't you say, hey, look, here's this function, right, f, but x must be greater than or equal to 0. Okay, if I add this right here, this is what we call a domain restriction. I am restricting what you are allowed to plug in. And now you are not allowed to plug these in. And then we should not get this having to go back, right? Now let's graph this. Let's look at the graph of this. What would that graph look like?
Little lines going straight up.
No, this right here, this parabola, what would it look like?
Just the right half.
Just the right side of it.
Just the positive.
Just the positive right side. Because look, we can still plug in 0, can't we?
Yes.
0 squared is 0. 1 squared is 1. 2 squared is 4. But see, we're not allowed to plug in negative numbers. I said it right here. You're only allowed to plug in 0 and positive. That draws me just the right half. That passes the vertical line test. That passes the horizontal line test. And that's why the inverse would exist. All right? So that kind of clever domain restriction allows us to kind of get around the fact that that didn't have an inverse by just cutting off part of the graph. Now, did I have to cut off the left side? Could I have left the left side alone? Yep, but what do I have to do? What would I have to do? Cut the right side off, right? Exactly. So here's another option I could have used. All right? So I could have, if I wanted to, come over here and say, all right, check out this function here. I'm going to call it g instead of f. Call it x squared, but this time only allow you to plug in x's that are 0 or negative. This is going to be the parabola, but just the left side. You can only plug negative numbers in. Can't plug in the positives. So you get this. Passes vertical and horizontal line test. So right now, if I ask you, does the function f of x equal x squared have an inverse? What would you say? If I just tell you, if I give you a function, f of x is x squared, does it have an inverse? You would say no, assuming that your domain is its implied domain. When we don't say what the domain is, it's what we call the implied domain. The implied domain is basically all numbers that don't cause this to go crazy. Like as long as you don't have division by 0, square roots of negative numbers. So the implied domain of this is all real numbers. So if I ask you if x squared has an inverse, you would say no. But you could add to that, say no, unless you restrict the domain to just positives or just negatives. Could I restrict it any other way? How about this? Could I do this? Could I say, here's a function x squared. X, how about if I just do 1 less than or equal to x less than or equal to 3? Would this be a function that has an inverse? Let's try and draw it. Where does it start? 1, so I go out to 1, I plug in 1, I get 1. Understand? Go out to 2, I get 4. Go out to 3, I get 9. Way up there. And then it would be the parabola in between, wouldn't it? But it would stop there and stop here, and it would just be that little section of the parabola. Does that section of the parabola pass the vertical line test? Does it pass the horizontal line test? Yes. That little piece of the graph is a function with an inverse. Make sense?
Yes.
Let's go even further with this. I like this one. I really like this one. This is going to help us a lot when we get to the sine and cosine. Can you help me draw something here? For this particular example, this one right here. Go back to this good old picture here. The domain of f, right? F goes this way. What's the domain of f in this picture? Everything between 1 and 3. So can I do this? Is it okay if I write this notation? It's the interval, everything between 1 and 3. That makes sense to you? What's the output? What's the range of f? Yeah, so look at this. It goes from 1 up to 9, doesn't it? It's everything between 1 and 9. And therefore, the inverse function that goes backwards, which we said exists because you can tell the vertical and horizontal line test both pass, I can plug things in to the inverse that go any number between 1 and 9, and it's going to send it back to something between 1 and 3. What is the inverse function of this function? The square root function. So if we wanted to know what the inverse of this function was, it would be the square root of x, right? But we would have to restrict its domain. What would we restrict its domain to be? Between 1 and 9. Okay. I need like a good nod of the head or thumbs up or anything. Do you all understand what I've done here? Yes? Question? Oh, just thinking of what it would take to undo an x squared, right? So like if I'm trying to take, 3 gets squared, it turns into 9. If I'm trying to take 9 back to 3, I'm going to take the square root. Good? So what I've tried to demonstrate here is that even if we start with something that in general does not have an inverse, if I restrict the domain sufficiently, then I should be able to get an inverse, at least if I cut off part of it. Yeah? And when I do that, I have to pay close attention to what's going in and what's coming out because those domains and ranges have an impact on each other, right? All right. I think that's good. Let's start with sine. So here's my challenge to you now. I'm going to draw a sine function up here. And I'm going to try and challenge you to figure out where we should cut it. Where should we restrict its domain so that we get something that passes the horizontal line test? So I'm going to draw it right here. I'm going to draw this a couple of times. So here's my first. Here's sine x. I'm going to call it f of x because it is a function. And we all know where it gets cut, right? We all know where these points are? Okay. Where would you like to cut this so that we get the whole thing? Pi over 2, where? I heard pi. So let's see if we all agree that this would work. If we cut it at pi over 2 and we stopped here at 3 pi over 2, and I'll do this in red, then we would just have the graph that starts up here at 1 and then comes down like this, goes all the way down to -1, and stops. Everyone agree that that little red piece right there would be a function that has an inverse on that little piece? Yes? Now, could I have gone just from pi over 2 to pi?
Yes.
And just done that? Would that little piece have an inverse? Yes. Could I have gone from pi over 2 to, like, let's say right here and just done that little red piece? Yes. Our challenge is to try and get a piece that contains the entire range. So we want to get, what's the range of the sine function? -1 to 1, right? We're trying to cut it in a place where we get the entire range. So if I only cut it halfway, yes, that has an inverse, right? It's a function that has an inverse, but it doesn't get the whole range. This nice cut from pi over 2 to 3 pi over 2 would get the whole range. So I like that. I like that. Is that the only one?
No.
Okay, can you give me another piece that I could cut? I'll draw another picture. So this, I'm going to say this checks. This could work. We're restricting our domain between pi over 2 and 3 pi over 2. Another option.
Negative pi over 2 to pi over 2.
Okay, you want me to go negative on that? I'll do that. Hold on.
Basically start at the bottom and go to the top.
So my other option that's being proposed here, here's my sine curve. You want me to actually go backwards to some negatives. So this goes backwards like this. And you're saying, since this is negative pi, this is negative pi over 2, this is pi over 2, and this is pi. So you're liking the idea of cutting it at the low point, right? And then cutting it off at the high point. Here to here. So I'll put the domain restriction up here. And this little piece. So we all agree that piece works too? You've got a function right there. It's got an inverse because it passes the horizontal line test. It contains the entire range of the function. So I like that candidate too. Are there more?
Yeah.
I could keep going, right? I could draw another one, go further down the number line and pick another piece. So as mathematicians and as human beings, okay, when we were trying to think about these inverse functions for these trig things, we got to this and we realized, well, you know what? What if, today I decide I'm going to use this one, but Zach decides he's going to use this one, right? And then that's going to cause problems in our mathematics because think about it this way. All right, let's see if you can. What the domain of this one, right? The things that go in are between here and here, right? Aren't these the things that come out of the inverse?
Yep. Yes.
Right? So if Zach's using this one, the things that come out of his inverse have to be between here and here. But if I'm using this one, the things that are come out of my inverse are going to be between here and here, and they aren't the same thing, right? And that's major problems. So we all had to agree. Yes, in history, humans have been able to agree on things before. This is one of the things that we agreed on. We all decided where we would agree to cut the sine function so that we all use the same inverse, the same piece. And the one we use is this one. Now, did you give me negative pi over 2 just because you were thinking about it, or had you seen that?
Well, you said it earlier. You said remember.
Okay, I did. Okay, so you remembered it. Good. You remembered it from what I told you. That's the one we choose. This is just as good, okay? But we just said no. This is the one, all right? Yeah, there's some negatives, but it's still, it's still good.
People like to go bottom to top and top to bottom.
Yeah, but the cosine's different. So, okay, we'll get to cosine in a second. All right. Got it? All right, so I'm going to formalize all this. If we restrict the sine function, oh, that's that red marker from yesterday. I had this really good red marker, but it doesn't erase very well. And it leaves this red that's never going to come off the board. All right. I think it's this one. Nope, not that one. Okay. If we take the sine function and restrict its domain, sorry, to the interval negative pi over 2 to pi over 2, then we get a function which has an inverse and this is a very big part of this. When we're cutting it between negative pi over 2 and pi over 2, not only are we getting a function that has an inverse, we also have that f attains its entire range. Attains its entire range. That means it's going to get everything. The outputs are going to go from -1 to 1. Right? You're going to get everything out of this function. You didn't cut it too much where you know, like if you cut it just there, you don't get any negatives out. So it's a perfect cut. Not too much, not too little, just the right amount. Its inverse, I'll continue here. Its inverse is called the inverse sine function, or the arcsine function. You'll hear it called different things. Hey, that's the inverse sine function, or hey, that's arcsine. You'll hear both phrases when referring to the inverse sine function. And it has a special notation. All right, here's the notation. So, if f of x equals sine x, that's just the sine function, then f inverse of x is written one of two ways. It's the sine function with the little -1 up there, or arcsine, not without the e, arcsine x. Those are the notations. You're either going to see this or this in textbooks. I must admit that I use this most of the time because it's less letters to write, but this is actually bad notation. The inverse notation that we have in mathematics is one of my least favorite notations in all of mathematics, because usually when you raise something to a negative power, it really means to drop it down. So you might think that that's like 1 over sine, but it's not. What is 1 over sine? Cosecant. So if I want to talk about 1 over sine, I'm going to use cosecant. If I want to talk about the inverse, I'm going to use this notation. Don't confuse the two. All right, we good? Does this all make sense? It feels like it made sense when I explained it. No? Okay. All right, so let's try and do some problems with arcsine. Just some very basic things first to start. First example. Find this without a calculator. can somebody explain in words what it is that I should be thinking when I see that? Like what am I?
The one is the y, you're looking for x.
Say again?
The one is the y, you're looking for x.
Close. 1 is the y coordinate, right? Because it's a sine function, right? This thing comes from a sine function. So remember, for a sine function, maybe I can draw it with a picture. With the sine function, sine of x, I'm plugging something into the sine, right? Aren't these angles?
So it's a theta.
Right? These are angles, right? And what it does is it spits out a number. And that number is always between 0 and 1. I mean, sorry, negative 1 and 1. And isn't that the y coordinate on the unit circle? Y coordinate unit circle. So that's what the sine function does. Takes in an angle, spits out the y coordinate on the unit circle. Here, the inverse sine function is taking in the y coordinate on the circle and asking you to give the angle that it came from. Right? So what is the angle that corresponds to 1 for your y coordinate on the unit circle? Pi over 2. Everyone agree with that? So look, I'll draw the picture. Here's the unit circle. Where's the y coordinate 1? Right here, right? That's where your y coordinate is 1. I'll put the point, 0, 1. So your y coordinate is 1 here, and the angle here is what? Pi over 2. So the answer to this should be pi over 2. Now, we learned that angles can be equivalent, that as long as we wind up back at that same angle. So could I have gone backwards and gotten to this angle? What would that angle be? If I went this way to here, what's that angle? Negative 3 pi over 2. Could I have put that as my answer?
Yes.
Are you sure?
No, it's outside the interval.
Okay. What did we say? Yeah, what did we say about restricting things?
We're inside the interval.
We were only allowed to be looking at angles between where and where? Negative pi over 2 and pi over 2. So you know how I drew this circle just now? What I want you to imagine is that you're never allowed in these two quadrants. Because this is the angle 0, here's pi over 2, here's negative pi over 2. So if you try to get to this point, the only way to get there is to rotate by pi over 2. You can't go this way because you pass through that band region, so to speak. And you can't go around more than one time and back because you pass through the red. So the red restricts you. Understand? That's us cutting the sine function so that we can have an inverse. Let's do another one. What is arc sine? I'll use different notation just so you can see it. Find arc sine of negative root 2 over 2. So this is saying to you, hey, on your unit circle, you should have a y coordinate somewhere that has a value of negative root 2 over 2. Right? And it wants to know the angle. So here's a way you should do it. When I'm doing these arc sines, I mean, when I was first learning them, now I can usually do them in my head because I can see the circle. But if you're not there yet, you draw this, you say, okay, I want to know where my y coordinate is negative root 2 over 2. That actually happens here and here, doesn't it? Those are the two places where your y coordinate's negative root 2 over 2. However, because this is an arc sine function, you must restrict yourself, and you're not allowed to play in this place over here. This is off limits. This is the adult zone. Okay? You stay over there in the kiddie zone over there. What's the angle? 7 pi over 4? Wait a minute, how do you get to 7 pi over 4? Oh, you went to the adult zone. You can't go over there. You're not allowed. You have to rotate this way. That's a negative angle. Negative pi over 4. Understand? See, this is a good thing. This region that's crossed out, this is a good thing because one person's going to say the answer is 7 pi over 4. The other person's going to say it's negative pi over 4. We get two different answers, and you wind up, well, what happens? Nothing, I guess. Did y'all ever hear about, did I tell y'all about the probe, the Mars probe? No? So many years ago, y'all know that we've like landed rovers on Mars and they've like driven around and picked up stuff and, right? But before we even did that, like, I can't remember how long ago, I think it was like 15, 20 years ago maybe. We were just like, here's Mars and here's the Earth. Okay, Earth, Mars. And we were sending out probes. We were just trying to get something to get into orbit around Mars so we could like take pictures and take readings, try and figure out where we wanted to land the rovers. And we were just starting to explore Mars. And we sent this very expensive probe out to Mars and we lost it. We didn't know where it went. We found it finally. What happened was instead of going into orbit around Mars, it just did just a direct impact into Mars and we lost it, okay? So they went and they tried to figure out, what happened, there's a lot of money and blah, blah, blah. Well, it turns out you had engineers from Europe and engineers from the United States working together on the project. And Europeans use metric and US uses US. So someone forgot to convert somewhere from metric to standard or the other way around. So we had some calculations were off. And so we lost the probe. I guess my point is that if you're getting 7 pi over 4 and I'm getting negative pi over 4, it's probably going to cause a problem at some point, right? So this restriction gets us all on the same page. We're all going to get the same answer, right? I don't know if that is a good, but it's true, right? This stuff happens. I haven't taught 1414 in a long time, college algebra, but I've taught 1314, which is the other college algebra. Not really. Okay, so you have, it's on paper it may look the same, but it's not. Okay, so here's my two classes, 1314 and 1414. So 1314, I say, okay, we take the square root over here. And then when you take the square root, you can't forget to do plus or minus 2, right? Because if you do that, then I'm probably going to take off a few points and, that'll be it. So that's 1314. 1414, I say, okay, here, remember, take the square root, you have to do plus or minus, right? What happens if you don't do plus or minus? Children, buses full of children fall off of cliffs that were poorly made. Planes fall out of the sky. Hundreds of people die. Wings fall off of planes. This is important for engineers. Not so much if this is your last math class. This is the same sort of thing here. Like, these things are important. Maybe they don't seem important now, but they are important in the big picture of things. We all have to agree on something or else we get different answers. Isn't that kind of what's beautiful about math, is that we should all get the same result? Like, it's not like an English paper where I write this paper and it's like someone's objective opinion of it, right? Now it does get objective and it does get, somewhat gray later, but we won't get into that. All right, how about this one? So I want a volunteer to tell me, to try and explain what it is they're doing in words in terms of the unit circle. Anyone want to volunteer? Please, not all at one time. We'll do one at a time, please. Go ahead.
So they try to find the inverse of
They are. You are. You are trying to what?
find the inverse of 0.
Okay. So what are you thinking? Why though?